last time on ENGR315 open paren R, close paren, and we were talking about deflections of beams and kind of going after something that looked, an equation that looked something like that. So bending stiffness, or the elastic modulus times second moment of area times vertical displacement is equal to the double integral of bending moment with respect to x plus some constants of integration. Remember this from last time? Yes? Cool. And actually, this would be a little bit more intuitive if I wrote bending stiffness on the other side, because vertical displacement should be inversely proportional to bending stiffness. Like, if that's higher, we shouldn't bend as much, right? It's straightforward. So at any rate, we had this, and which we said that as long as we can come up with a expression for the bending moment, we can integrate the crap out of this, and life is good. The only trick being that we have to utilize appropriate boundary conditions in order to solve for these constants of integration. So today we're going to be talking a little bit more about what those boundary conditions might be and how we could apply them to something like a statically indeterminate beam. So last time we had something like a cantilever beam, force at the end. You could find out an expression for bending moment, and it would be something like that-ish. And you get an expression for that. But the question would be, what combination of at what x location do we know what the vertical displacement y of the beam is going to be? Right, at x, for a cantilever beam, it's kind of a gimme that at x equals 0, y is going to be 0, right? We don't really know offhand the displacement of any other part. That's what we're making this equation for, right? But we can also know the slope at the wall. We know the slope of the neutral axis, which is the same thing as if I found that. If I find the derivative of this equation, it's the slope, right? That's what we went through, like the tangent function, how it's equivalent to the slope, which is equivalent to the derivative. And at the wall, if you have a fixed boundary condition, that slope is always 0. So that gives us two different cases. So we can set up this so we can have two different equations to solve for two unknowns. So we can get those constants. Now that's well and good, but the trick comes when it's not as straightforward. So what about something like this? And let's ignore that guy for a second, because I don't want to complicate this. So we have two unknown reaction forces. Say this is for, if you want a free body a diagram that this came from, would be something like this. And then, excuse me. Oh wait, sorry, that's actually not there. That's just a representation of the which called the dotted arrow in the middle is just a representation of the distributed load. How you can treat that load as one concentrated load of the same magnitude at the center of the distribution. Remember that fun thing? That which called they're just saying, hey, you can do hey you can do that. Excuse me. So here we have one end that's fixed onto a wall and one end that has some sort of pin joint, so it's allowed to rotate. And what's the problem here? Can we solve for all the forces and moments? Okay. So let's try to do that then. So let's call this guy FB, call this FA, MA, in case you can't read it. There it is big, there it is bigger. This distribution is some function of x, w, so that's like some weight, some force distributed over a distance. Cool. So, how do we solve for it? Go. Okay, so let's get some positive directions going. Okay. What are the forces we got in the y direction? I know we have some of them, but can we get all of them? Okay, so FA and FB are positive. Is distributed negative? Okay. And the magnitude of that distributed load? W is his kind of like it's kind of like a linear density of it. It's a force per length. WL? Yeah, times length. Yeah, because it's weight per length or force per length. Okay. Okay. Oh, we still got two unknowns. So, we've got two unknowns in that equation. So, what else are we going to do?
So, B is a thin joint, you said?
Yep. So there are no moments created by that joint.
Then I think we should.
Okay. So, what are all the moments?
There's one created by FA.
Which is? Yes.
There's another one created by
MA, which is in the positive direction. Okay. And what else?
W.
And that direction is? Sweet. I think you're correct. That's all of them?
I think so.
I think so too. All right. So is MA a support force? A support moment? Remember our diagram? There's like we have beam that's fixed, and there's a pin over there. So all these guys come from that support there. This guy comes from that support there. How many knowns do we have here? 3, which is one too many. We only got 2 equations. Are there any other equations that we can make? The answer is, lucky for us, yes. It's just not a force or moment balance on the external structure. So what we can do is make some more room. Say, okay, I can find out what at least two of these things are in context of a third, right? So like I could solve this guy for MA. Like I can get MA equals FAL minus WL squared over 2, right? And I can solve the other equation as FB equals WL minus FA. And put everything in terms of one unknown, right? That's just math. I thought I erased you. Go away. Thank you. Okay. So from these, I can also, if I decide to take a section, say here, that's probably a lousy color to do it in. It's probably mildly better. If I decide to do something like this, FA, MA, there's my F shear, bending moment, sorry, I'm going through the top. There's my distributed load. Let's call it from this. I can make a expression for the bending moment, right? Now it won't be. I won't be able to just plug in numbers because I don't know what FA is. Like I'm always going to come back to an unknown. But that's fine. And I can make an expression for bending moment in terms of all that all goes back to FA. So if I wrote that out, it'd be something like summation of moments equals negative MB minus FA x plus MA x plus W x squared over 2, something like that, right? That'd be the summation of moments at that section. And if I wanted to, I could substitute in everything that MA is, right? So I have an expression that's totally in terms of FA, or the force at this support. Well, based on based on that, if I find an expression here for MB that's like this, I can just stick that into the expression that I had before. I can just plug that directly into there. Now, here, how many different boundary conditions can I find? How many different places along this beam can I say exactly what the displacement is, as well as what the slope is? 2. Let's be more exact. So what boundary conditions can I specify? B. Okay, so what's a boundary condition at B? Oh, if I measure x from the left-hand side, x is L, yeah. But yeah, y equals 0. So you might say, like, if I wanted to give coordinates for this, it'd be L0. I know that because the thing's pinned there. It has to be that. What about here? What's boundary condition for this side? Say again? In terms of displacement. Yeah. And what about in terms of slope? At the left-hand side. Right, also 0 because it's fixed. So dy dx also equals 0. Because it's called because it's a fixed boundary. We said that's the model of the beam. So this side cannot rotate. That's why there's that reaction moment there. So we said this side is fixed. Because it's fixed, it's stuck to that wall. The section that's at that wall is fixed to that wall. So that section right at the wall is parallel to it. So that means that the neutral axis is perpendicular at that point. So we have 3 places that we can specify a boundary condition. How many unknowns do we have now? 3, right? We got that guy, and we'll have an FA pop out of that. So by substituting in these boundary conditions, we can solve for everything in this equation, and you'll see that as you add more complexity to the boundaries, like if I said that this end is fixed and there's some reaction moment there, well, I just got, besides the displacement boundary condition, I also got a slope boundary condition now because I've fixed that end. So generally speaking, the more unknowns that you get, the more ways you have to solve for them, because as you can incorporate these other bits of information. Same as when we dealt with strain and whatnot in statically indeterminate beams back in like chapter 2. All right, questions?
Why isn't there another force in the x direction that was A?
Say again? Oh, it's because this is really, it's actually 0.
Okay.
Like they put it there to say you could have one there, but you're not really. I mean, for large deflections you will, but we're not really caring about that right now because that violates our assumptions. Okay. Like if I summed all the force in the x, there's nothing acting else acting in the x direction, so it would be 0. Yeah.
So are we going to keep going with this?
This is kind of the end of it.
Okay, so what you plug in for MD is what's right above it?
Yep. Whatever your expression for bending moment is. Yep.
C1 would be
Constant of it's a constant of integration.
So really the equation is just mb dx dx, but then the constants come out once you integrate it.
Yeah. These came from the general. Hold this. If you really wanted to see everything pop out, you'd start from that. But yeah, we just did all the integration last time, so I skipped to the end. Yep.
so you don't actually plug anything in C1 and C2.
You have to solve for them. Yeah, you have to solve for them.
Solve for, right?
It's part of what we're solving for.
Yeah.
Displacement. Yeah. Yep. You need to find these other constants first so that you can figure out why. Or if you have extra forces, you need to solve for those too. in order to find y. Or you could just use this method to find those forces, whatever floats your whatever floats your boat. You can do a couple. You can do a couple of different things with the fact that with the fact that you can look at the displacement of a beam. Cool beans?
Very.
Sweet. It's like beans that have been soaking overnight in cold water, or more like ice water. Sweet. All right. So that's beams and beam deflections. Cool. There is a way to jump directly from a load distribution to a deflection. Unfortunately, I don't think we're going to have enough time to do it because I really want to talk about buckling. I might say I want to buck the curve or something like that. So if you want to look at it, it's in your book. It won't be on the test or anything, or on homework, but it's an interesting thing. Also gives you a fourth. Also lets you play with fourth derivatives, which are kind of cool to say you've done. Anyhow, that's it. So that's it for beam deflections. From here, we're going to start talking about buckling. And buckling's a really interesting phenomenon. That's it's still a little bit of a mystery in certain applications, and really trying to look at it more. But what buckling is the failure of material well before it's failed in yield. Meaning that if I had a column, say, made out of whatever this plastic is, and I started to push, so I'm pushing my hands together, I want this column to stay in a straight line, right? Like, that's the purpose of a column. You don't make them so that they bend, right? I'm pushing, and I haven't torqued my hands, I haven't twisted them, but the tube has started to bend. And you might say, okay, whatever, that's just because the tubes kinked to begin with. But you can do the same thing with a whole lot of different things. Like here, if I press down hard enough, you see how this is starting to bend too. That's if I was making a column to stay straight and to support something, the fact that it's kicking out to the side and is about to collapse is a failure, right? Like that's not desirable behavior, and it's going to destroy whatever I'm doing. In fact, it'll cause the column or the beam to destroy itself. So that's an example of a buckling failure. It's a mechanical instability of the column that causes it to fail well before its actual yield point. So let's see if we can explain this a little bit more. So if I had a beam and it started to bend a little bit, so like that, right? And like that would be like a straight line from end to end, and say that I'm only applying a compressive load to it. And I'm applying that compressive load as close to the center of it as I possibly can. I'm not trying to cheat here and push it like off to one side so it bends. This is absolutely dead center. And as we saw, it can make these things start to bend through a form of mechanical instability. So, if I take a section here, right in the center, have some shear, we have some bending, we have P being transmitted. Okay. So you have a shear force, we have a bending moment, and we have some axial load all being transmitted. This is all the same as when we talked about eccentric loadings, right? Like if you had what's called the open carabiner that was being pulled apart, or what's called a C-clamp that's being tightened down. This is the same sort of load disk, same sort of internal loading that we saw there too, right? Well, if we take moments, what I want to say is, yeah, it's called, if we take a moment around the section, the same as before, we can see, make sure I'm doing this right. So I need to get some dimensions in order to be able to finish the equation. Which we can kind of see that which is called the force at the which is called the force at the end is going to create a moment around that section, right? And this part's just the moment arm of that force, just P around that section. All right. So we can get how this would how this would occur, right? You just as soon as the beam deflects a little bit due to whatever and from what I understand anyhow, it's a somewhat random occurrence. What's called the axial load that you're applying is going to start to load is going to start to bend the beam, and it's just going to be limited by, bless you, and it's just going to be he limited by the stiffness of the beam, how far it deflects. And the further it deflects, the worse this is going to get, right? So you might think that it's called that because of the bending stress you're producing here, and when that, bless you, and when that's going to cause yield, that there might be some like critical load or that you can apply to the beam that's going to cause it to really kick out and fail, right? Does that make sense? Can I show you that? Yes, no, maybe? Okay, cool. Okay, all right. So it's called the point here is that there's some critical load, and if you work out what's called if you work it out, you can get that critical load, that critical axial compressive load, to be something like this. So pi squared here times the bending stiffness, because it's a failure in bending divided by the length squared. So as length increases, what does that mean for the critical load? Okay, it comes down. As length goes up, critical load comes down. What does that mean for our failure point? Will we hit it sooner or later? Say again? Sooner, right. If the critical load is lower, that means that as I keep push harder and harder and harder, I'll hit that load sooner than I would if the beam was shorter. Yes?
So it's like long, slender objects are more likely to buckle.
Right, kind of, which you can kind of intuit from here, right? Like if I have a really short piece, like I'm pushing the crap out of this, and it's not really going anywhere. But if I have a really long section, like I push a little bit and the thing bends.
Which I guess makes sense since it shows up with that square.
Right. So if you wanted to also look at this from like a stress point of view, stress is like force over area, right? So I can do something like that. And for say like a circle, I would be pi over 4r to the fourth. And if I wanted to rewrite that in terms of area, I could say like pi r squared over 4, right? So I can rewrite this as like a critical stress equals pi squared E A r squared over 4 AL squared. Bam, bam. Okay, so I'm moving this into like a critical stress, so like a critical force. And it said, well, for a circle, this is your second moment of area, right? And if I wanted to pull like a pi r squared, like an area out of that, I could do that, right? That's just a group of numbers. Maybe. There we go. And that gives me that. Because I have area in the numerator and the denominator, I can get rid of area entirely on this side and regroup it one more time to get something like this. So pi squared E divided by 4 L over R her quantity squared. Where this guy, what's called the L over R, you might hear referred to as something like a fineness ratio. Which, just like I was saying, essentially describes how slender the object is. So this is a more formal way of stating what we can also see intuitively, that the more slender an object is, the more likely it is to buckle. And this doesn't only apply to circular things. I mean, you can work this out for a rectangular cross-section or any cross-section that you want. You'll get the same kind of result. It's just easy to show with a circle. All right. So buckling, it's going to occur before before her yield potentially, and it's all based on essentially this fineness ratio and how stiff the beam is. All right. So if I wanted to kind of say that one more time in a different way, if I wanted to make a plot of failure. Whoa, my goodness, let's try that one again. If I want to make a plot of failure stress, so this is like axial compressive stress, and this is like fineness ratio, and this is yield stress. It might look something like that, where as my fineness ratio gets smaller and smaller, or the object gets shorter and fatter, I'm going to start approaching my maximum axial compressive stress is going to approach my yield stress, which makes sense, right? It should. However, the more slender my object becomes, eventually it's going to reach some critical stress that it's going to fail at before it hits yield. So that's just kind of another way of looking at this. All right, cool. So let's look at a couple other things. So the trick is, what would buckling depend on? Control. What would make that critical stress change, both conceptually, or yeah, conceptually speaking? Say again. What the object is. What do you mean? Say again. Okay. So on a list of things that vary your critical stress, you have Young's modulus, and that came out of the equation. So based on what? So based on what the material is. What else? Okay, dimensions and cross sections. So that includes our fineness ratio. And everything that feeds into the second moment of area. What else? What else might do it besides what was mentioned in the equations? Think of it more conceptually. You have a beam that's trying to bend. What could make it more difficult for the beam to bend? Magnitude of the forces, right? Well, that's called. We're looking at things that vary those loads, vary where the critical load is, and magnitude of forces doesn't really do it. Okay, what do you mean by fixed? Okay, so the boundary conditions matter, because like if I have this beam, say, and I'm holding the two ends so that they must stay straight, you might think that'd be harder to bend the middle than if I was just if I allowed both ends to flex, right? Then it'd be relatively easy to bend the middle because there's nothing really resisting it. So how we describe the boundary conditions is going to change how, or when rather, a beam buckles. And it's actually somewhat in-depth to find all those. So I'm just going to give you the equations for it and talk briefly about how you might find it. All right. I was going to say anything else about this? I don't think so. So this should be ratio, not ration. Cool. All right. So yeah, besides the material itself, also the boundary conditions. So here we go. All right. So the way that we treat boundary conditions. So if you have our equation here, EI for L squared, is that we can treat different boundary conditions as having a different effective length. So whatever the actual length of the beam is, we can find some multiplicative factor to make an effective length based on whatever the boundary conditions are. For example, if I had a beam that was fixed on one end and free to move on the other end, if you worked out the math for it, it would actually be the same bending expression as if you were looking at a column of twice this length. And so the effective length is actually 2L for what's called for a beam that's fixed on one end and free on the top. That if you work out the math, I promise it does work. Okay, I'm just kind of running through it because we're running out of time. On the other hand, okay, so if you have fixed, free, 2L. On the other hand, you could have something that's fixed on one end and pinned on pinned on the other, and this and the top's being pushed down. Hold on. So that'd be like fixed, pinned. Actually ends up being 1/2 L. You might think of it as how do I want to say this? So this guy would actually be more susceptible to buckling than the fixed free eggs key case. Make sure I'm on the right page. Yes, I am. Cool. Yeah. Oh, sorry. That's I thought that there was a different value for that. That's fixed. Wrong place on the page. So that's if both top and bottom are fixed and they're being squashed together. Cool. For the fixed pinned case, so back to this. So let's go back to this. So back to this guy. It's actually kind of cool. You can if you work out the math, it actually ends up being a linear second order differential equation, which I know that you love. But unfortunately, try to hold yourself in. We're not going to solve one today. And it comes and it works out that the effective length for that square 2/2 of the original length, so like 0.707. So you might think of this being less susceptible to buckling than the fixed case, and so on and so forth. So that's pretty much all I got for today. Are there any questions? Yes.
If you have like the laminated material and you try and put normal compressive forces on it, will it have different yield stresses for the compression and extension?
Okay, so for a laminated material, it depends on how thick it is. So laminated materials obey the same laws as everything else. The trick is more so this. Short answer to your question, yes. Long answer to your question, say that I have some glass, like fiberglass, there's some glue, fiberglass, glue, fiberglass. That'd be like a laminated material, be like your typical composite. And I apply some load to it. But because the glue is not as stiff as the glass, if you go back to if you go back to like chapter 1 or chapter 2, who because they all have to strain together, they're at different they're at different stiffnesses. The stress inside the material is going to distribute itself according to the stiffness of the different layers. So you'll end up with like lots of stress here and just a little bit of stress here, which actually ends up which actually makes shear stresses a problem, right? Because you're changing the effective load that's on each individual lamina. So while it could fail in while it could fail in buckling, there's a larger chance that it's actually going to there's a significant chance that it's actually going to delaminate first, that each of the reinforcement layers of the glass is actually going to peel off of each other before the whole panel fails. So it's actually a really interesting question that's really hard to answer.
Would it be stronger in that direction or 90 degrees?
It depends. Put it this way: this, as pictured, is really, really weak going this way. So you might think, if this is like a fiber, it's really easy to cut a fiber. It's really difficult to pull it, right? So so the only thing that's really holding this whole thing together in the perpendicular direction is the glue, which is the weakest part of the whole structure. And in fact, when I was making unidirectional composites in undergrad, so stuff like this, you could bend the crap out of it one way, but if you looked at it wrong in the other direction, it would break. Yeah, it's kind of wild stuff. So that's your 2 cents of composite.